All right, so the next configuration is called a delta to delta. This is when you have a source in a delta configuration and also the load in a delta configuration. So the figure below shows a delta configuration. The equation previously discussed can still be applied to solve for the currents and the voltages. However, pay attention to the relationship of the phase and line current as well as the phase and line voltages up in this configuration. So we always want to be mindful of that square root 3 and whether or not if we're going to be adding or subtracting 30 degrees because of the lagging or leading. So we still have to take that to consideration like we did before. All right, so here's the example. For the circuit above, let the load impedance equal 50 ohms at an angle of 60 degrees and determine the following. The phase voltage, the phase voltage of the source and the load. The phase voltage of the source and the load. So right here, we're trying to find the voltage across the source, and we're trying to find the voltage across the load. All right, so note, since the source and the load are both in the delta configuration, the line voltage equals the phase voltage for both the source and the load. Because this source is connected across lines A and B. Same thing with the loads. This load right here is connected across A and B. Same thing for the other two phases. So all the phases for the source and the load are connected across two line voltages. All right. And so therefore, let's see. So it's given that, so what this problem gives you is the line voltage. So it says EAB equals 100 volts at an angle 0. So this is my reference voltage right here. So therefore EAB equals VAB, which is equals to 100 volts at an angle 0. And the other two phases are displaced just by 120 degrees. So therefore we can use Ohm's law to calculate the phase current by just taking VAB, your phase voltage across your load divided by the load. And so in this case right here, we it's equal to 2 amps at an angle of 60 degrees. Apply the same formula for the other two phases. Now, that's the current that's flowing. If we're talking about load AB, that's the current that's flowing from here through this load right here. So remember, this line right here, this line current is not equal to this load current because it's being split at this junction point right here. But we have to take that into consideration. By using this formula down here. So I line is equal to IAA, which is the square root of 3 times this phase current. And when you're going from a phase current to a line current, you have to subtract 30 degrees. And you apply the same method to the other two line currents. All right, so the next configuration is a delta to Y. So this is when you have a source as that is connected in a delta configuration and is supplying power or to a Y load. So notice we don't have a neutral wire for this type of configuration. But because we have but because we are considering that this load is going to be balanced, our calculations can still be performed in the same manner like we once did for the other configurations. So basically a delta Y is just like a Y delta network previously discussed in an earlier example, except the delta is the source and the Y is the load. So here's an example. Determine the following if the load impedance is equal to 10 ohms at an angle of 35 degrees and the line voltage is equal to 500 volts. All right, so in order to find the other line voltage, the magnitude remains the same. The only thing changes is the phase angle, which is displaced by 120 degrees. All right, so note the line voltage is equal to the phase voltage of the source in this configuration. So just like before, I mean this phase voltage of the source is connected across two line voltages. Two lines. It's connected across two lines. So the line voltage is equal to the phase voltage of this delta source. All right, so the load phase voltage. So in this configuration, you have to convert the line voltage to a phase voltage. Don't forget about the relationship of line voltage to a phase voltage, which you have to keep in mind of the square root 3, and then subtracting the 30 degrees. So for this example, well, we know the line voltage is 500 volts. So we divide it by the square root 3 to get a phase voltage. And once we subtract 30 degrees from it, from this line voltage, we can now determine the phase voltage of VAN. And just apply the same method for the next two phases, VBN and VCN. All right. So before even jumping into this one, the one good thing about this configuration is the line voltage is going to equal the phase voltage because the line current is going to equal the phase current because the current is flowing through the line. There's nowhere other place for it to go but through the load. So therefore, the load phase current is going to equal the line current.